Hello, hello. Whoa. Hey, I'm here today. This is fantastic. Hello, everyone. Oh, come on, try that again. This is Google I/O. Come on, hello, everyone. There it is. Now, I don't know if you guys know this. Hopefully you do. This session's being live recorded and broadcasted on the intertubes right now. Hopefully we won't clog them up with all of our awesomeness. Now, when I pitched this talk a couple months ago, I said, hey, I want to talk about this HTML5 game, and to demo it, I actually want to have some skydivers jump down and come in and give a talk. And they're like, sorry, we can't do that. We did that for the keynote. So next year I'll do skydiving. Hello, everyone. My name is Colton McAnlis, and I'm a developer advocate here working at Google, focusing on Chrome games. And today is really cool, because for you guys, this is Google I/O, and you get a lot of information. But for us Googlers, this is a holiday. This is a magical event for us, because all year long, we toil and we struggle, and we write tons of code and throw tons of code away, and we spend all of our time making products that we can't talk to any of you about, except today. And today is a fantastic day because I get to talk about a project myself and a core group of people have been working on, and that's a game called GRITS. And GRITS, first off, it has robots. Pretty cool, right? Everyone love robots? Hands up, robots. Love it. Yes. I think there should be more robots on the internet. That's my personal opinion. So let's talk about where GRITS started. GRITS is a player versus player game entirely written in HTML5. A couple months ago, I gave a great talk. Well, I thought it was a great talk. I didn't get promoted afterwards, but still went over quite well, on best practices in developing an HTML5 game. And the talk effectively highlighted issues that game developers were running into when developing HTML5 and kind of how to overcome them. Someone came up to me afterwards and they said, this is a great talk, where's the source code? Dang it, you got me. We just talked about ideas. So at that point we decided, hey, let's actually write a full player versus player game in HTML5 and open source it and bring the results to Google I/O. And that's what we're here talking about today. So in order to make sure that a bunch of Googlers didn't run off into the distance and do something crazy, our managers made us specify some bounding parameters on what kind of video game we were going to make. So first off, we want to make sure that it was multiplayer only. We're going to be a small group with a small amount of time. We didn't have artists. We don't have designers. We don't have the ability to create a 56-hour expression of our inner angst, represented by you riding a horse and slaying a dragon. Let's keep it to multiplayer only, where robots shoot robots in the face. Like, super easy, right? Second off, let's leverage Google technologies. As you guys have, I hope, been hearing today already, and because you're here at Google I/O, you're probably already very aware that Google provides a suite of powerful technologies. And a lot of game developers out there actually don't know how to use a lot of the Google technologies and translate it into their game development process. So for GRITS, what we wanted to do was highlight those technologies and provide source code on how to properly use them so that we can actually say, hey, here's a game that actually works and it's using App Engine. Here's the source code. Or hey, here's how to use Wallet the right way. Here's the source code. Thirdly, we wanted to contract our art and sound. So Google's a big company, but we're predominantly engineer heavy. We don't have a lot of 3D artists and designers sitting around. So we actually tapped a great company called Fuzzy Cube Software to do all the art for our game. So big round of applause for those guys. Come on, give it up. It was kind of funny because we came in and we're like, hey, we need a ton of art in like 6 days. And they're like, okay. And finally, and this was one my manager actually made me put on the slide, was our intent was not to make this product commercially viable. This was intended to be a source code repo that everyone in this room can go grab and start making player versus player HTML5 games. We're not trying to take on all the big names of the industry out there. We're really trying to prove that this is something we can do. In order to do this, I actually tapped game developers who work at Google. So these are developers who used to be in the industry, shipped games on console and PC, who now work at Google. In addition to that, we also grabbed a couple people who were experts in the subject area we needed so that we can actually get sort of a full-fledged team. Consider GRITS a view of traditional game developers looking at HTML5 as a viable platform. And hopefully the discussion that we're going to have today is going to highlight some of the things from that particular perspective. Again, we wanted to bring our results here. We thought this was the proper platform. And from the start to finish, we only had 120 days. And I'm sure everyone in here has heard of Google's 20% project, right? Hopefully, yeah? That basically means that we're only allowed to work on this 1 day a week. So really, for the 120 days, we only got 1 day a week. But with that short amount of time, what we found was the APIs and the technology available in HTML5 allowed us to do some amazing things. So let's talk about what we actually were able to do. And I'm going to cut to a video because I've been having internet trouble all day. Let's see if I can do this. Maximize. Is there a button? Oh, full screen. Come on. There we go. So what you're looking at here is sort of the login screen. We allow players to use Quick Game or log in. We have full G+ integration, so that when we log in, you actually see my friends list and my circles there on the side. You actually see my name and my portrait, and we've got that nice little share button, which allows you to share the game to the live stream and tell people what a great thing you're doing. Now, you noticed I actually misspelled GRITS, so I decided not to share that one. It's a little embarrassing. For our game, we actually support keyboard layout and mouse, so that you can actually play on your laptop or on your desktop. When you run into the game, you can configure your robot first. And this is sort of phase one of a longer strategy here. You can pick primary, secondary, and tertiary weapons like a chainsaw, landmines, shotgun. I think I get the energy sword here. Energy sword is the bomb. If you're playing the game, always choose the energy sword. It's plus 10, uber awesome. We kind of go into a little montage here to give you an idea. So we're a top-down game. There's a little bit of a lag on the delay. It's not that choppy and live. But basically, it's robots shooting each other, right? Everyone loves that, right? This is why we get up in the morning, to see robots shooting each other. Effectively, you see a little bit of the jittering here. That's due to latency and networking correction. We've got energy items that you can pick up. We've got health bars, names. You can actually see the anonymous players running around in the universe. You can see the bullets bouncing. Energy shield, awesome. +1 on energy shield. Like sometimes you wish the +1 button were bigger so that you could like hit it so hard it'd put a dent in the wall, right? When you find something cool? Nobody else? No one? You're at a Google conference and you don't applause to a bigger +1 button? Okay. There you go. Hey, in the back, get that guy a t-shirt. But anyhow, this is more of our gameplay, running around, and of course, I died at the end. Now, that little QR code in the top there, we're going to talk a little bit more about that in a minute. So that is the demo. So what we're going to talk about today is how we built this product, how we put it together so that you can walk out of here understanding how you actually make player versus player games with HTML5 and then can go off and make awesomeness on your own, because that's what I was all about, right? So let's start about the top. The player part of player versus player is the most important. So in a traditional game developer sense, when you want to get a bunch of computers simulating a game together, the easiest way to do it is allow each game to actually simulate the state on its own and then transfer the state to all the other machines. This model is actually called a peer-to-peer networking. So each game actually independently computes all the physics, math, position of rockets, explosions, power-ups, sends it to all the other clients, which receive it and say, OK, this is your game state. Now, in the early 90s, this was the predominant way that games actually did multiplayer networking. And we've thankfully moved away from that for a couple of reasons. Number one is this methodology is actually really prone to lag or high latency. So what will happen is, in a player versus player or a peer-to-peer network, if any single player actually starts to slow down or their connection is bad or the machine slows down, you miss a whole load of data that has to be synced between all the other machines. And the only real resolution to that is actually to halt the other players in the simulation or slow them down as well. And so if any of you played some classic first-person shooter games from the 90s, you'd get that little disconnected icon in the corner like, hey, wait, we're waiting for someone to tell us what's going on. Another problem with the peer-to-peer networking model is it was massively prone to cheating. So what would happen is a single player could say, hey, I just picked up the rune of Antioch, and I'm now invincible for the next 12 days. And all the other players would have to abide by that information because that's the way that peer-to-peer worked. Thankfully, again, we've moved away from this. What we use today, and this is what GRITS is actually built on, is a technology called Authoritative server. So instead of the clients actually calculating the game state themselves, we actually allow a centralized server to calculate all the game state and then send the results down to the clients. At this point, this means that the clients are really nothing more than dumb terminals. All they do is take an input, send it to the server, receive game state, and then render the results of what the server tells it to do. This is a lot better. First off, it fixes our cheating problem because the server is authoritative. It tells you who has the rune of Antioch and whether or not it's a 12-day buff or a 6-day buff and whether or not there's a DPS spell at the end of it. But that's a separate discussion. Gamers. Secondly, it also fixes the lag problem, right? If any single individual actually drops out of the network or experiences bad latency, what happens is we don't have to slow down the other players in the simulation. We just have to let that guy go do its thing, and the server assumes that it hasn't received any new input. So this actually creates a better quality of gameplay for the rest of the people in the simulation. This is actually pretty much the architecture that most multiplayer games are built on today. This includes all of your RPGs, MMOs, FPSs, Most RTS games, real-time strategy games today, are actually still built on the peer-to-peer network topology, simply because there's so much data to actually simulate. And then they get around the cheating issue with some other craziness that is way beyond this talk. Now, because we have an authoritative server, we run into a very specific problem. And that problem is server compute latency. So let's say you're running on the client, and you actually say, hey, I want to move my robot forward. That input is actually sent up to the server. The server will then take some time to compute the new state, and then the state is then transferred back down to the client, where the client receives it, updates its information, and then hopefully displays it to the user. The problem with this is that the time between input move and update state from the server is going to always be longer than it takes for the client to actually render the next frame, or at least you hope that you're rendering at 60 frames a second and you're not getting packets that fast. The result of this is that you actually get really choppy animation. So if we got our little robot on the bottom here, and we just only update his position when the service tells us to, he'll pop into position A and then pop into position B, if my clicker works. See, clickers, it's awesome. Now, to compute, will she write if I say that again? Yeah. I found a new toy. I want to actually do the rest of the talk like this. Sorry, I'm messing with the people typing. Anyhow, GRITS computes this with something we actually call client-side prediction, which means that while the server's actually computing the game state, the client will compute the same game state in parallel. And what this means is that after the user issues the move command, that's sent off to the server, and the server will compute the state, but the client will also compute the state. This actually allows us to do a smooth animation between the next position so that the user actually doesn't see this lag created by sending packets to the server. And that was supposed to be animated, but something happened, and so the arrows mean animation. Use your imagination. You guys are smart, I think. Aha, she wrote it. Cool. The cool thing is that's on the internet live right now. Like, someone's like, he's insulting the audience. So anyhow, that's the basics of how player versus player games work. Now, let's talk about the things that GRITS does specifically, because GRITS, of course, is an HTML5 game. So what you just saw is applicable to C++ games and everything else in the wild. GRITS, being HTML5, had to do a lot of things different. Let's dive into that a bit. Clicky. Clicky. So let's talk about our architecture. First off, our client information, which consists basically of our HTML data, our JavaScript, our sound files, and OGG, everything else. This is actually served on top of App Engine. So we actually serve all the content. Our domain is a .appengine.com domain. And we actually store and communicate to App Engine also to store our database information. So the number of kills you get, the number of credits you have, how many times you use the energy sword of awesomeness to frag some other dude, that's all stored on the server. Also, if you look at the code, you'll actually see some traces of information about how to do unlockable items. One of the first updates in the patches that we want to do is show you how to do unlockable items using wallet and credit transactions and all these other things so that you guys can just grab that code and put it into your games, making more awesome games. The client will also communicate to Google+ as well as Google Analytics. You saw in the video that Google+, we grab your friends' information, we can actually link to the page, we can post to your stream. The Analytics one is actually really cool. So for those of you in here who aren't game developers, there's the concept of being able to track what your users are doing at pretty much every second of a game. So what we actually do in GRITS is when a player dies, we actually log that data to Google Analytics. We actually fire off a custom event, and that's stored in the analytics system. Then later, what we can do is come back and say, hey, show me the map, and show me where all the deaths have occurred in the past 72 hours. The cool thing about this is that it allows our designers to take a look at the map and you go, hey, you know what, there's a choke point right here. There's probably way too many deaths. I'd like to change the map a little bit and move things around. It also tells us things like how many people actually use the energy sword and whether or not we should get rid of it entirely. And we drive all of this data collection through Google Analytics. So it's not just for webmasters trying to figure out if half of their traffic is coming from Asia or if it's coming from Slashdot. We can actually use these custom events to get real information about what our players are actually doing in our game and provide a tight feedback loop to make adjustments real time. We use NodeJS. NodeJS fans? When I was taking notes and when I was like, I need to write a talk, there's probably going to be robot fans and NodeJS fans. Check. Our backend actually runs Node.js out in the cloud, running on a compute server. And our client communicates to our game instance, our Node.js instance, using Socket.io through Websockets. And there's a cool fact of the matter that Websockets are actually sort of a TCP variant with a much safer UI, or much safer API. Now, the client will also do some other interesting communications. You'll notice that when I clicked Quick Game, or wanted to join a game, the client and the server actually communicate to a matchmaker. Now, this is actually one of sort of the advents of the last 15 years of game development process, is the fact that people realize that if there's a 12-year-old kid sitting in some area where he doesn't have to go to school all day and can just sit there and play games all day, and you hop on for a match and you're matched with him, he's going to destroy you, and every time. And that's not cool for you, because he's all like, haha, I'm only 12. And you're like, hey, dude, I got a job. Lay off me. And he's like, you smell. Or at least that's what my last weekend was like. Anyhow, what matchmakers do is they effectively attempt to try to match players of unique skills, put them together in buckets, find open games. Effectively, it's this massive combinational backend that figures out how to slot people and combine them in ways that make their experience in the game a lot better. So we actually have a matchmaker running for GRITS that runs entirely on App Engine. And the cool thing is, we're not going to talk about this today, but you all need to go to the talk by Fred Sauer called Gaming in the Cloud. And I think, actually, that time is incorrect. I think it got moved again. But anyhow, go to Gaming in the Cloud. He's going to talk about all of the App Engine side of GRITS, including that interesting QR code. One of the things Fred did was actually write an Android controller for GRITS. And so if you actually scan that QR code with your Android phone, you can actually play the entire game using your Android device and connect it to your PC. So you use this as sort of a controller. So definitely check out his talk. He's a cool guy. At the core of our simulation is a fantastic library called box2d.js. And what you're looking at here is sort of a mock-up of a top-down setup. Box2d, or rather, when you look at this, you see a game, right? But in reality, it's comprised of a lot of box2d primitives. In green here, we have the physics objects representing collision. You can't shoot through these things. You can't walk through these things. The red squares here actually represent in-game objects. These are teleporters. Box2D has a fantastic callback system in that as you intersect with two items, or as a collision occurs, we get a nice little callback and we can respond to it properly. Which means for us writing GRITS, we actually can be pretty lazy about what kind of code we write. We actually don't have to write interesting simulation loops or anything. The only code we really write is how to spawn an object and what to do when it hits another object. So when a user touches a teleporter object, we know that a user is touching a teleporter, and then can make the appropriate change to teleport him to whatever position he's at, or into Zool Alpha 90, which is a cool place. You should check it out. We also use a great concept that Box2D provides, which is the collision filtering system. So anytime we actually launch projectiles or objects or spawn a new member into the game, they're assigned a team. So what you're looking at right there is the red player actually, or the player there is actually on the red team firing projectiles that are attached to the red team. And of course, subsequently, we have the blue team. This allows us to actually say, hey, don't do friendly fire, right? So if you got a team, all of red team, you don't want to get shot in the back of the head by your teammate, Box2D handles all of this for us. All we have to do when we spawn a projectile is specify don't intersect with anybody else who's got the team red flag. Again, completely hands-off on our part. We're so super lazy when writing this project. Box2D did all the heavy lifting for us. The explosion up there is actually the same process, is that again, a projectile intersected with the wall, and we computed what those two objects were, and then decided that the proper result was to actually spawn an instance of an explosion. Again, Box2D is awesome, use it. Now, one of the issues that we ran into while having Box2D as well as client-side prediction is prediction adjustment. So what happens is, as the client says, I would like to move forward, the client can go off and move forward. Well, the problem is positioning is actually driven by Box2D, which means that the server can actually disagree with where you're supposed to be at. So the client thinks he should be there, while the server says, actually, you should be along this vector over here for some whatever reason. Let's say you're running into a wall or something, or a demon is chasing you. I don't know why there'd be a demon chasing a robot. That seems weird, but just go with it. So what we do is a process called prediction adjustment, where over time, we'll actually modify the forward vector of our moving robot slightly towards what the server has told us we should be at. So what happens is, after a couple of frames, we correct our position just enough where the player actually doesn't see that they're getting a discrepancy between the client and server. This actually allows us to hide a lot of the latency that you would normally see from the client and server, the authoritative server communication process. Now, if the client and the server position differ by some extremely large value, we'll just snap, because at that point, it's like, oh, we're 15 frames away, and it would take too long, and it doesn't look good. So we do have sort of a catch-all in case we get too far ahead. Now, one of the other things, this was, we actually found this like last week, so I'm glad we fixed the bug before my talk. Yay! is our authoritative server actually has to drive the client in more ways than we were originally predicting. So let's say you're running the client here, and you choose to fire a missile. I think that's the proper pronunciation. And the client says, hey, this missile has intersected with this object. Well, again, remember, the client is computing game state in parallel. So the client actually says, hey, this guy's there. Well, the server says, no, he's actually over here. So now we have a mismatch. The client has said a collision has occurred. The server says, no, you're wrong. And so what we do in this situation is we actually say, I'm sorry, client, we're not listening to you, right? Because to a player, if they saw a collision, they would expect to see health go down or some sort of validation that they're doing the right thing and killing their fellow robots. But instead, what we do is we ignore the collision and actually let the bullet pass through. This is really important from a game player perspective. There's been a lot of research over the past 10 years about doing multiplayer prediction and adjustment analysis and what players actually can perceive as the problem versus actually being the problem. And actually saying, hey, we're going to ignore client-side predictions is hands down the perceptive correct solution from all the game players. So if you're writing games, make sure you do it this way. Or not. It's up to you. You can write games. You're smart. So let's talk about networking. What are the things that we did specifically? How many of you have actually written like TCP networking code in C++? A lot of hands. I'm proud of this room. This is an awesome room. We should like fight the other rooms and prove how awesome we are. I think we'd win. Anyhow, so in C++, what you usually end up with is some sort of structure that you define like this. A flag for what kind of packet it is, 32 bits for the data, and let's say a float, a direction packet. And then this would be communicated between client and server, because sooner or later in C++, this is usually in a header file, and you would cut a server build versus a client build, right? Well, let's say you've got a junior programmer who comes in and says, I didn't want to listen to you anyway, I'm going to change the header structure. And I'm going to push a client build without updating the server. Well, now everything's broken, right? We no longer have the same packet structure, all the data's getting out of line, and this is a massive problem. GRITS solves this with a really unique solution that I felt was super important to talk about. What we actually define is, rather than defining the structures themselves that are then copied between client and server in builds that we cut, we actually define a proto-structure. So what you're seeing right here is the input structure. We say who it's actually from and what direction you're going. It's specified as strings. We're sort of proto-defining what this class should be, or struct, or whatever it is in JavaScript. I'm not a JavaScript guy. What the server actually does is when an instance boots up, it actually parses this JavaScript file, reads this proto data, and actually runs code generation on it. So rather than actually generating the structures, we actually generate a whole suite of functions, an API set, that allows the client and the server, well, the server specifically, to actually use that as an API, push data in, and the APIs will actually properly pack the bytes in an efficient manner into what the structure would be. Now, here's where the cool part of JavaScript comes into play. We actually pass this code-generated set of APIs down to the client. And then on the client, we just call an eval function. So this means that our client and server will always be in sync when communicating with each other. There is no possible way that they can actually get out of sync, because as a client connects to its server, it actually receives all of the information on how it's supposed to communicate through these API packets. This is actually really cool. It's one of the few things that I love about JavaScript that you can't do in C++ for game development, right? You can actually say, here, use this. Now, once you're writing this code, especially with multiplayer games, you end up shooting a lot of bullets. Sooner or later, you're going to just sit there and hit the button. It's kind of like that button masher when he's fighting playing a Street Fighter game. It's like, you're not hitting any buttons, but you're still beating me. I hate you, and you're 12. Yay. What we actually found was in our original implementation that in about a second of gameplay with a full 8-player session, we'd send about 6.2 megabytes of data. And that's position information, directional information, index data, what state it is, rotation, all this other stuff. So we needed to address this really quickly, because I'm sure, again, everyone here is at Google I/O, you're internet developers, you understand this graph, is that if I've got a 240 millisecond window, and I've got really fat packets, the number of packets, or rather the information update from the server that I get, is limited. So in that 240 milliseconds, I can only get so much data from the server to tell me about the game state. I can only update my information so fast. Instead, what you want to do is create smaller packets, more concise information, so we can receive more of them in that short window so we can update the game state quicker. Because again, since the server is doing the entire computation, we need to ensure that we receive the updates as fast as possible so the client can stay in sync. Now, one of the ways we do this, clicky, is actually using packet grouping. So usually when you send a packet down a wire, there's multiple levels of the technology stack. And each level that your packet runs into usually adds a little bit of overhead, right? So socket I/O will add some bits to it, the TCP layer will add some bits to it, maybe the operating system will add some bits to it. Well, what happens is you actually end up with a lot of data that you don't need, right? And for these individual packets, this actually adds up to a bit, a significant amount. So what we do is we actually have a heuristic set that defines the ability to group all of our packets based upon memory size. So what we say is, hey, we're going to queue up our packets until a time limit has elapsed. So if we only get one packet and let's say a second has elapsed, we just go ahead and send that on. Or we'll queue up all of our packets until it reaches like a megabyte worth of data, and then we'll send that down the line. What this does is it actually reduces all of the additional overhead that's added by each of these layers. This is really a critical thing for us because we send a lot of data. One of the other things we do, or another set of things we do, is actually duplicate packet reduction. So we do this in two ways. The first is that we understand that the people writing the game are not thinking about the networking layer as they're writing the game, right? So as we're going through our update loop, as all the items are updating themselves, sooner or later you're going to have someone come along and assign a variable to A. And then 20 loops later, it's going to assign it to C, and then some time's going to go by, and then you're going to assign it to B. Well, what we do in this situation is we actually track these state data and updates over time, and we only send the latest update. So what will happen is we'll say, hey, if the variable's already been set and we're setting it to something different, forget the other state. Don't put it in our packet grouping, right? This keeps the client from doing redundant state updates, because otherwise it would have to do C, B, C, A, and then finally B, which it doesn't need to do. Another thing we do with our stateful tracking is we actually analyze whether or not the state that we're about to update a packet for is identical to the state that already exists. So if a line of code comes along and says, let's set the position to A, and the position is already A, then the server won't actually update that data, won't send it to the client at all. Now, with the packet grouping, as well as the duplicate packet deduping, that's a Dr. Seuss rhyme, I should write a book. We actually modify our situation quite significantly. We end up going from about 6.2 megabytes per second to about 1.3, which is a lot better in our situation. So these are like 3 super easy things that had really nothing to do with the technology, but had a lot to do with our analysis of how our game was molesting the networking stack and sending packets around. So let's talk about rendering. HTML5 is awesome. I always thought this was a great quote that no one really laughs at, but world domination often starts as a misunderstood napkin doodle. Like, I don't know if you guys walk into a bar and you see some weird doodle, like, oh, that looks like a dinosaur attacking Manhattan. I've got an idea. Or at least in my mind, that's how it works. So again, let's go back to our mock-up screen here. Again, you've got a bunch of things, you got a bunch of pretty pixels that are being displayed. In reality, this is broken down, is that this is actually our background layer. Our background layer is a bunch of 64 by 64 pixel sprites that an artist has placed together on a large sheet, and we actually render that data. On top of that, we actually render our player avatars, which are animated sprite sheets. And then all of our projectiles and explosions are also animated sprite sheets that are blended using a different composite layer. In order to do this and stay performant, we actually heavily use the concept of atlasing. Now, in the games industry, we call it atlasing. I know in the HTML5 world or web development, you call this sprite sheets, right? Sprites? Nods? I don't see a nod. Everyone asleep already? Cool. That dude gave me a thumbs up. Get him a t-shirt, too. Thumbs up for t-shirts. Anyhow, we actually atlas everything. In fact, what you're looking at here are the only 3 atlases we actually use in the game. That's it. Everything, every piece of art, all of our menu data, all of our in-game sprites are packed into these 3 textures. And here's why. With one atlas request, let's say you've got a 4K by 4K texture, at about 100K of information total, your total transfer time, as measured by the Chrome developer tools, is about 240 milliseconds. So this is nice, right? We've got a 4K by 4K texture. It comes down the line pretty quickly. We can actually decompress it, get it on the screen really fast, get it into the canvas renderer, and we're doing good. Now, if you were to say chop that 4K by 4K texture up into let's say, 4096 individual requests. So each one is about 10K each at about 64 pixels by 64 pixels. What you end up with is about 4.3 seconds of total load time. And the reason for this is kind of two to threefold. Firstly is that any given client connection to a server can only have so many open connections. So if you've got 4,000 connections sitting around waiting to happen and your browser is only allowed 6 at a time, basically everything gets stacked. And what you're looking at in the Chrome tools here is that transparent line, the long bar there, is actually Chrome being blocked by the server saying, I'm sorry, you can't get this file yet because we're still waiting on something else to complete. So with all of these loose assets being requested, you slow down your load time significantly. Now, you also notice at the end of the line is the little opaque circle. That opaque circle actually represents the time once we've actually received the file to decompress it, get it on the screen, do all the other stuff, which is a really fast process. We lose we lose 4 seconds just in waiting around for Chrome to do more connections. So in reality, using atlases saves your load times significantly, which again, a lot of web developers are starting to notice this. So stop using leaf assets. Stop doing it, or the robots will get you. Now, when our artists made our original map, they actually came to us with a pretty small set. They said, hey, we're going to use these 64 by 64 tiles, and we're going to draw them everywhere. And we said, that's fine. So when you look at the screen, you should really look at it like this, which is sort of how the rendering engine looks at it, like a bunch of little tiles that are rendered onto canvas. Well, the issue we ran into was that each one of those was actually a separate draw call. And for each draw call, you have sort of an implicit API overhead that's involved with the draw call. Now, you'll see that there's actually some nice blends here. We've got a green background, we've got some of the tiles, then we've got some more of the little hexagons that are blending on top of it, and then we've got a dent in the universe, and then a little thing there. That's like 5 to 7 draws per quadrant there. Now, this adds up over time because artists want to make really pretty art, and that's usually accomplished by compositing layers of art on top of itself to create this really rich environment. Well, again, this doesn't work for us, right? If you've got a high-res monitor and a lot of screen space, there's going to be a lot of draws, and a lot of machines can't handle this. So what we did to counteract this is actually use the concept of off-DOM canvas, where rather than actually rendering each of these small tiles at runtime, we create a canvas object that's not attached to the DOM, and actually render each of these tiles into that canvas. And then later on, we can simply do one draw call, offsetting that large canvas wherever our viewport happens to be. This actually was a huge savings for us. On some of our Linux machines, this actually took our frame rate from 2 frames a second back up to 60. Like just this one change. So it was about 10 minutes of code to get us that frame rate back, which was fantastic. Of course, then the artist came back and said, oh, by the way, I've got a bigger map for you. And then we ran into a different problem, which was now that we had a 24K by 24K pixel map. And we were doing one draw call every frame for this massive pile of pixels. And that put us back at 2 frames a second. So all of my work was for naught. To counteract this, we had to do something different. So let's say we've got our little viewpoint there in pink, because hot pink is the cool thing to do on the internet. Hot pink is the cool thing to do on the internet. Cool thing to do on the internet. Cool thing to do. Oh, man. Sorry, when you find a toy, you just got to play with it. Anyhow. What I actually do is I actually create, in order to combat the fact that this one draw call actually puts too many pixels on the screen, because the canvas actually just does a dumb draw, right? It doesn't say this pixel of this subtexture is or is not in your viewport. It just blits the whole thing to the screen and lets the GPU figure out, for hardware accelerated canvas, lets the GPU figure out the details there. So what I actually do to combat this is we actually chunked up our environment. So when you're actually playing in the large maps in GRITS, we actually chunk it up into 1024 by 1024 tiles. Now, this heuristic of 1024 versus 2048 or anything else was actually sort of just done by trial and error. We effectively said, this looks good on this Linux box, and this Linux box is not powered. So what this allows us to do is where we were doing one draw call for the little pink box, we actually do 2 draw calls now, but it's significantly less pixels that the disband process has to actually deal with, or more importantly, the GPU has to deal with this, rendering and clipping and figuring everything else out. Now let's talk about the tools. So when you're writing games, actually taking a step back, let's take a step back. So as a traditional game developer, I was a game developer for about 10 years in the industry, worked a lot of really cool places doing really cool things. One of the most important things that I worked on consistently was creating really good tools that allowed designers and artists to create amazing content that really caused people to buy our games. Now, in my opinion, one of the biggest drawbacks to HTML5 as a viable gaming technology is the lack of good tools to allow content creators to create great content. Now, I'm not talking about the language here. I'm talking about the ability to create content in a way that content creators can reflect with. So what we did with GRITS was we didn't try to reinvent the wheel. Rather than trying to create HTML5 specific tools, we went back to the basics and used tools from standard C++ game development and just made sure that the data was read in by HTML5 properly. This started with a great tool called Tiled. Tiled is a free, open source-ish map editor on the internet. It uses Qt as a primary rendering or a UI engine, so that means it runs cross-platform. Now, Tiled does some really cool stuff. What you're looking at here is actually our atlas of our map sprites, and then, of course, our map next to it. So you can actually go in and fill in your sprites and use cool brushes and use a blend effect and fill things together. Tiled also allows us to create collision objects, or just objects in general, and then we can flag them with collision values. So what you're actually looking here is the polygon tool actually specifying out that, hey, this is some object in the environment. And you can see on the side of the map over there that this is actually the collision layer, right? So when the game reads it in, it says anything in the collision layer we make an actual physics object for that you can't shoot through or run through or teleport on top of or use the rune of Antioch to destroy, which that last one's actually super critical. The other cool thing that Tiled allows us to do is set properties on objects. And this comes crucial into play when we do things like teleporters or quad damage or picking up energy capsules. Because what it allows us to do is put a little box on the map and say, hey, this is a spawn item and this is a health box, right? So we can actually specify all of that stuff inside of Tiled. We don't have to write custom code for this. In fact, the designer and the artist can use this tool exclusively, and then it just spits out a nice JSON file, which Tiled does, by the way, that we read into our game. And the client and the server both read this information, so we know where collision objects are, we know where teleporters are, and most importantly, we know where quad damage is. Because if you don't have quad damage, you're losing the game. Pro tip. You tweet that. Pro tip, IO12. The next tool we actually use is a great tool called Texture Packer. Texture Packer is probably one of the most advanced tools I've seen for actually taking a whole bunch of small textures and packing them into a big atlas, and then passing that data off to you. Now, what you're looking at on the screen here is all of our assets are actually listed on the side over there. So the artist literally grabbed them all and dragged them in the tool. Then what you see in the middle window is the result of Texture Packer putting it all in. Now, one of the really cool things that Texture Packer does is we'll actually analyze the true boundaries of an image. So let's say you make a 64 by 64 texture, and then you put like a 5 by 5 little sprite right in the middle of it. Well, Texture Packer will actually analyze that image and realize that the true content bounds are actually 5 by 5. And it'll actually crop it and only put the 5 by 5 image in the map. And then it'll spit out in a JSON file what the original bounding values were. So by using Texture Packer, you're actually optimizing the number of pixels used by your artists. Sometimes artists don't make the best optimized artwork. Maybe. This is also really cool, too, is that we actually had to break up our in-game assets versus our start menu assets. That's why we actually have 3 atlases, right? So this is actually all of our menu data. It's in a separate atlas so that we can load it and do all of our rendering in HTML or in the DOM. So all of our menu stuff is done in the DOM, and all the gameplay is done in the canvas. So we can actually load this atlas ahead of time, use CSS, use sprites, use transition. I think you guys saw impress.js moving the menus around in there. And that's all loaded before you get in the game. And then once we get in the game, we can load the other 2 atlases. So we reduce load time, reduce pixel latency, and really it's all given to us by these 2 simple tools. So the lessons. Let's talk about what we actually learned in this process. So first off, can you do player versus player in HTML5? Absolutely. Some would say mission accomplished. I'd plant a flag or hang a banner or something like that, but they wouldn't let me put pyrotechnics on the stage. I did ask. After they turned down the skydiving thing, I was like, well, what about pyrotechnics? And they're like, stop talking. I was like, OK. Anyhow, you can absolutely do player versus player in HTML5. It's a fantastic ability. We've got canvas rendering. We've got hardware-accelerated canvas rendering. We've got WebSockets. We have the ability to manipulate the bytes that are sent over the line, which is probably the most crucial thing in bandwidth reduction and latency optimization. Really, it's there. We can do it. From a game developer perspective, the HTML5 APIs were not built for games. HTML5 was built for a web to transfer data and do rich content, but they weren't built for games. The good news is that they're starting to change. As you've probably already seen, Chrome has been very proactive in adding APIs for game development. We've added full screen support, mouse lock support. We've added gamepad support, which usually when you say, why is Chrome putting in a gamepad? Am I going to use a controller to navigate my Facebook page? No, this is because we're putting in games. We're being very proactive about understanding that games, more than any other technology, push the boundaries and push the envelope. And trying to be a modern browser, Chrome is very aggressive about this. For a player versus player game, bandwidth reduction is crucial. In fact, it's the only thing you really need to worry about in the world, right? Hiding the latency from the user, reducing the number of bits on the line, this is a full-time job. Now again, we only had 120 days. We had some really great results out of that. You should probably spend a lot more time optimizing that system if you're putting out a commercial product that you're going to use. Also, this sort of piggybacks in it is that the client-side prediction algorithm, and I encourage you to go Google this. There's tons of papers out there by tons of first-person shooters and MMORPGs and any of the game developer conferences out there saying, like, hey, we solved it this way. I highly recommend you take a look at the GRITS source code, see what we're doing, compare that against what the industry is doing, and figure out a proper technique to use for your game, right? What we provide should be considered a boilerplate and a starting base, and then you need to move into more advanced versions after that. WebSockets work really well. In fact, I would say probably we had no problems with WebSockets. Once we moved to Socket.io, it was just easy. We used it, we sent packets, we received packets. It was fantastic and easy to use. As I said before, Canvas, we did all of our rendering in Canvas. A hardware-accelerated Canvas in Chrome is really fast and really powerful. And we didn't want to write a full WebGL engine, period. We didn't have time to do it, right? We didn't have time to worry about atlasing or UV sets and whether or not we were rendering middle of polygon versus edge of polygon and what's the GPU doing and out of process. No, hardware-accelerated Canvas shields us from all that information, but gives us the same performance, which is great. So if you're writing a 2D game in Chrome, consider Canvas first. And then if you run into performance problems, optimize it until you absolutely have to go over to GL for it. Now, if you're doing 3D, definitely go to WebGL. You can't do Canvas 3D easily. Definitely take advantage of oft on canvas to accelerate any large bitmap stuff, right? If you've got a lot of static data that's being rendered per frame, make sure you do that, but definitely make sure you segment it because the artist will keep generating content that's going to make it harder and harder for your frame rate to be what you need it at. Again, use atlasing, right? Going from 270 milliseconds for the load time to 4.6 seconds is crazy, right? Especially if you're doing this stuff on mobile, right? Where usually on mobile, if my site takes more than a second to load, I've already thrown the phone across the room and started drinking heavily. Like, again, that's my Saturday night. That doesn't have to be your Saturday night, right? Utilizing HTML5, utilizing the DOM to do all of our UI was a huge win. Coming from traditional game development, we have a ton of packages and middleware out there that we spend a lot of time trying to sort of bend C++ into the will of our UI system. The fact that HTML5 comes with the DOM, the most advanced, sophisticated UI system in the world, Galaxy. I'm going to say Galaxy because I think it's that cool. That was a huge win. To ignore that or try to reproduce all of that stuff inside of Canvas don't even try. It's not even worth it. So the game is live right now. It's actually been live for 2 weeks. Game's live. gritsgame.atspot.com. You can go play right now. Hopefully the servers are up. Maybe they're not. I don't know. We'll find out soon. The code is live. code.google.com/p/gritsgame. Go get the code. Start hacking on it. Please submit issues, submit bugs. We'd love to hear what you're breaking and how you're breaking it. We had a great question a couple weeks ago from an internal Googler who said, hey, do you mind if we write an AI system that cheats? And I said, please do. And then send me the patch. More importantly, go to the Chrome sandbox. Check out a game called Strike Fortress. So what I've done with GRITS and what our team has done is a small subset of what you can do in 120 days. EA, Electronic Arts, has had a team working on a pure 3D HTML5 game. And they've been working on it for a lot longer than we have. And it's in the Chrome sandbox live right now that you can play. And the coolest part is you can actually go up and scan the QR code and start influencing the game with your phone. So while two people are standing there actually playing, we're utilizing the full power of the web by letting other developers actually drop bombs on people on the phone. It's a fantastic product. The guys have been doing an amazing job. Please leave this session, walk right over there and play it, and tell them I sent you, because I get a t-shirt every time you do. I run out of clothes really fast. It happens. So with that, hey, thank you all so much for attending this talk. I'm excited to see what HTML5 is doing with gaming. I'm excited to see the room that's packed. We've got people sitting on the floor. Hi, I see you. T-shirt for those guys. My name is Colton McAnlis. This is how you get a hold of me. Thank you so much for the talk. We'll open up for some questions now. Please feel free to use the microphone. And before we do that, hey, big round of applause for the typey person. Yes. You're awesome. You're awesome with the typing. I'm a huge fan. Questions? Yes, sir.
Yes. What do you see the overlap with this and play-n? And also, how did you do the server-side emulation? Did you use the same JavaScript code to validate the state?
That's a great question. So the two-part question there, which you're cheating. You're only allowed one. Two-part question there. How does this overlap with things like play-n? And the second part is, how do we actually do our sharing or our computation of state on server-side? So the first one is play-n is a fantastic tool framework that works more with Java, to my understanding of it, to produce a sort of nice games middleware setup. GRITS is not considered an engine and should not be used in that vocabulary. GRITS is boilerplate code. This is a setup and a bunch of things that are not intended for you to use as an entirety, but a bunch of little small capsules that you can consume individually and then take the knowledge from that and build off of it. We're by no means creating a larger ecosystem here. We're just trying to give you guys sort of pebbles to feed the empire. The second question was how we're actually splitting our code client server. We actually have two metrics for that. So first off, we have an isServer variable that's only defined on the server-side code through Node.js. And so in our shared code that's actually included in the client as well, we can actually say, if it's a server, run this loop or run this set of code. If it's not the server, exclude it. Now, for some subclasses, we actually have, like, for instance, if you want to load graphics or do drawing, it doesn't make sense to have any of that code sitting on the server side. So in those situations, we actually split the code. And we actually have a server folder and a client folder, and those are actually separate modules that use object-oriented programming to inherit from the server-side classes. So fantastic questions. For a lot more of that, I really encourage you to dig deep in the source code. Check it out. I believe you're next, sir.
Yeah, a quick one about the source code. Has it been tested across different browsers as well, or has it been optimized for Chrome? And are the assets in the source repository as well, like the tile tools and the original graphics?
Absolutely. So the questions were, have we tested the source code across multiple browsers, and are the assets available in the source code? We haven't had time to actually test the code in other browsers. Right now, I just kind of hack out and say, sorry, this is optimized for Chrome. I can't fix the other issues in the time. The good news is that the assets for the game in their at-list form are provided in the source code under the license we provided it. We don't provide the PSDs or the originals because of some weird thing, but it's all there. And we provide the JSON files too. So you can actually scrape the JSON, scrape the atlas, and regenerate all of the loose assets if you'd like to do that.
Cool.
Thank you. You were next, sir.
Yeah, two questions.
You're cheating. All you guys are cheating. You're only supposed to walk up and say
like not a real question, then a real question.
Okay.
Why is it called GRITS? And then how did you do any kind of like automated testing for your game?
Okay. Why is it called GRITS? I'm a fan of GRITS. That's all there is to it, right? Let me put it this way. As a Google employee, you see a lot of projects come through with secret code names and stuff like that. And when you have a chance to name one, you kind of pick something kooky so that someone else didn't already steal it, right? Like you'd hate to have named your project Glass, and then have a dude skydive in and be like, here's some glass. And you're like, ah. So GRITS just kind of showed up one day. It's not an acronym or anything. And the second question was automated testing. We had some basic stuff to sort of test load balancing for App Engine, which Fred will talk about in his talk a little bit later, how to properly scale that sort of things forward. We didn't do any testing on the client-side code, and we didn't have a lot of time in our window to test the server-side code. So other than sort of mandatory play tests for all 6 of our team members every day, we didn't get a chance to get much of a big harness put together. So that's kind of a fault on our thing that we'd definitely like to see fixed. We're over here now.
Hi. You talked about some prototype language that allowed you to create both the client and server-side JavaScript. And I was wondering if you could speak some more about that, or where I can find out some more information on that.
Okay. Yeah, so the question was prototype languages that allow you to generate both client and server. Oh, so you're talking about the code generation that we do?
Yeah.
Yes, so look at our source code. That's actually the place. So it's not actually a prototype language. We actually define a structure in JavaScript and then use JavaScript to scrape that JavaScript and then omit JavaScript. So we use JavaScript to code gen and then send that file around.
So it's not a third-party library
Nope.
or anything like that?
It's all in our code base. In fact, the file you're looking for in the source code is server/proto.js. That's the exact file. You'll find our definition, and then proto-eyes, I think, is the one that actually does the scraping and the code generation after that.
Okay, thanks.
We're over here.
So since WebSocket is TCP only, did you guys have any kind of evaluation of TCP versus UDP and like how that behaves in a, when you have a real network conditions and packet loss and things like that?
So the question is, did we get a chance to evaluate TCP versus UDP versus packet loss and real network conditions and stuff like that? I would love to have somebody do that testing for us and let us know where it's falling out. UDP wasn't really an option that we're able to dive into a lot. I mean, we have WebSockets that are available. There's very rich containers and wrappers for that. So again, in standard C++ development, you run up into a brick wall of like, hey, there's no real good library for UDP. I have to reinvent the wheel every time. The fact that the JavaScript developer ecosystem is so vibrant with people putting out open source libraries, it didn't make sense for us to just reinvent the wheel there. It made a lot more sense to use things like Socket.io and take advantage of that stuff. I will say, though, that the guy who wrote all of our networking code, Craig Tiller, absolute genius. He's from the games industry where all he's done for his entire career is optimize server-side code and bandwidth and latency hiding and everything. So definitely contact him. He's that first portrait right there. Very beautiful man. Contact him. Craig, if you're watching. Yes. Yes, sir.
So how did you host your Node.js?
Next question. I like that. That was nice. Going once, going twice. The live internet feed, everyone's like, refresh. All right. Hey, thank you guys so much again for your time. I really appreciate it. Go check out the EA game. I'm Colton McAnlis. Send me an email.